Okay, this is our fourth complex numbers video. In this video, we're going to be looking at what's called the Argument diagram. Now, the Argument diagram is just a way to represent complex numbers. So we have it here in this corner. So basically, in the Argument diagram, your horizontal axis represents the real part of the complex number, and the vertical axis represents the imaginary part of the complex number. So if you imagine you have a complex number, z is equal to x plus iy, then it would be x would be the horizontal component and y would be the vertical component. So this would have the coordinate x, y, and that's it. So it's just a way for us to visually represent complex numbers. So complex numbers, z equals x plus iy can be represented as a vector xy on the Argument diagram. You can add and subtract complex numbers in the Argument diagram by adding or subtracting their corresponding vectors. So you add complex numbers the same way that you add vectors, and we talked about the nose to tail method for adding vectors. So here I will do an example. First one, we have z1 is equal to 4 plus I, z2 is equal to 3 plus 3i, and it says show z1, z2, and z1 plus z2 on an Argument diagram. So there's your z1 going along this way. So it was 4 plus I, so 4 along and 1 up. And there's your z2, and it was 3 plus 3i, so 3 along and 3 up. And your z1 plus z2 is a single vector which replaces them. So we've done it out sort of algebraically or numerically here. It was adding that real parts. The 4 plus 1 gives you 7. Add the imaginary part, 4 plus 3 gives you 7. Add the imaginary parts, and 1 plus 3 gives you 4i, and so that's what it would be. But you can see as well, it's the same as going along the z1 and then along a z2, or doesn't matter which way you add them, it's the same as going along the z2 and then along the z1. So just to go over that again, your z1 plus z2 is a single vector which would replace z1 and then followed by z2, or else z2 and then followed by z1. Okay, the next example is similar, but it's instead of doing z1 plus z2, we're doing z1 minus z2. So this z1 minus z2, I'm going to think of this as being z1 plus minus z2. So if you remember back to your vectors, if I had a vector which was just, say that was, we'll just call it z2. If that was z2, then z minus z2 is just the same, but it's in the opposite direction. They look like they're different lengths, but they should be the same length. There, those lines, but it's the same. It's just going back the opposite way. So again, in this one, there is your z1. There's your z2. So importantly, then this would be your minus z2. So the single vector which represents, so this vector here would be z1 minus z2, because I've gone along my z1 and then I've gone back parallel. So this is the same as going along my minus z2. So that's a single vector which represents. So that was z1 and minus z2. Or you could have done it another way. You could have gone, so this one, remember, is our minus z2. So I could have gone back down here, that's minus z2, and then I've got along z1. So whatever way you want to do it. So get rid of those wee markings there, and we'll go through that again. Okay, so just go look at that again. I've gone along z1 and then back along z2, minus z2, so along z1, back along minus z2, or else I've gone back along minus z2 and then up z1. And this single vector represents either of those, so z1 minus z2. Okay, next thing for us to mention is the modulus argument form. Now, we mentioned this in one of the previous videos. I think it was maybe video 2. So the modulus is just the length of the vector. So really, when you have it drawn in a length of the complex number, when you have it drawn on the Argument diagram, it just gives your length. So let's go back up and have a look at one of the ones we had earlier on, just to see how we could find this. So we're just going to look at we'll look at our z2. So here if we do this diagram out again, our Z2 was, it was 1, 2, 3 along, 1, 2, 3 up. So that's what it represented. So our Z2 was equal to 3 plus 3i. So if you wanted to find the length of that thing, you just could do a right angle triangle and you would say that's 3 as well. So the length would be equal to, and now you just say the modulus of it is equal to the square root of 3 squared plus 3 squared. So it is equal to 9 plus 9 square root of 9. So the square root of 18. And you put equals in your calculator, it would cancel that third down for you. Okay, so in general, if your z is equal to a plus iy, a plus ib, your modulus of z, or your length of z, is going to be equal to a squared plus b squared and square root. So you square the real part, square the imaginary part, and square root. Okay, and if these had changed, had these been x's and y's, so depending what way they write it, so had it been x plus iy, your modulus is going to be x squared plus y squared and the square root. So again, same thing, just square the real part, square the imaginary part, and square root. So back to our notes on modulus argument point then. So the modulus of a complex number z is written as either modulus of z or modulus of x plus iy, or r, and we'll be talking about that one later on as well. Okay, the argument of a complex number is the angle its corresponding vector makes with the positive real axis. So again, let's just do another example here. So say I had z is equal to 4 plus 3i, we'll just do. If I just do a diagram of that, what that actually looks like. Now you've got 1, 2, 3, 4. We'll just do 1, 2, 3. So there is my my vector z is equal to 4 plus 3i, and it's just we line it, the links that up. Okay, my argument is this angle in here. So to find that angle, again, you just link it up as a right angle triangle, and you'd say, so tan theta, is equal to opposite over adjacent, so it's 3 over 4. So so theta itself is tan to the minus 1 of the 3 over 4. Okay, so if you change this, and it was, instead of being 4 and 3, my x value, my horizontal, my real value was x, my imaginary value is y, it would be just tan theta is equal to y over x. So you can see this is where it comes from as well. Okay, a couple of notes then. The argument of a complex number z is usually written as arg z. It is usually given in radians, where 2 pi radians is 360 degrees and pi radians is 180 degrees. I know there's an example in one of the homework questions we'll do where it's given in degrees, but normally it is given in radians. So if they don't specify, definitely give it in radians. That makes it just more common for them to use that. Okay, so just, you can see again there, you put your x, z is equal to x plus iy, and you do the right angle triangle, your arg z is just this angle in here. Okay, very important thing then, the argument of theta of any complex number is usually given in a range from minus pi to positive pi. So this is sometimes referred to as a principal argument. So you find your angle between here, between here and here as what it is. Sometimes as well, let's say give it as a positive thing. So it's not always given as that. So say your angle was in here. So say your angle is in here. So for example, maybe it is your argument then, principal argument is minus 2 pi over 3. Sorry. Say your argument of z was minus 2 pi over 3. If for some reason, that would be typically the way it would be if it was back here, for some reason they ask you to give the argument as a positive number, you'd have to go all the way around to here. So as a positive, again, this isn't the normal way for them to do it, but they sometimes do. They ask you to give it this way, the argument would be 4 pi over 3. So how I've got that, it's a full pi plus another pi over 3 to get round, and that would be it. Okay, we're going to look at an example of this. Hopefully once we see these in example form, they will be very, very easy for you. Okay, example, z is equal to 2 plus 7i. Find the modulus of z. So for the first one, modulus of z, we'll just write that down again. Z is equal to 2 plus 7i, and modulus of z is what we want to find. So this is square root of 2 squared plus the 7 squared. So it is going to be equal to 4 plus 49, square root of all that. It is going to be root 53. And your calculator will not cancel that down. There's no good way, nice way of doing that one. Okay, your arg z then is equal to tan to minus 1 of, tan to the minus 1 of your imaginary part over your real part. So your arg z is tan to the minus 1 of 7 over 2. So that is going to be equal to 1.2924 ... and to 2 decimal places, 1.29 radians. Okay, just to go through where I've got that one from. There was my z, it was 2 along, and it was 7 up, and I'm going to call that alpha. For some reason they typically use alpha here, whatever, so alpha or theta, whatever way you want to use it, so I've used alpha this time. So tan alpha would be equal to 2 over 7. Sorry, that's wrong, I've done it the wrong way around. Yep. That was my point z, sorry, and it was, my real part was 2, I should have said. My imaginary part was 7. So it was tan alpha is equal to 7 over 2, so alpha is equal to tan to the minus 1 of 7 over 2. So that's where that comes from. Okay, next one says find the modulus of z again. So same idea as before. For this one, we'll just write down our z is equal to minus 4 minus I. Minus 4 minus I. This is not playing ball here. I'll fix this whenever I'm saving these for you properly. So minus 4 minus I. So your modulus of z is equal to minus 4 squared plus minus 1 squared and square root of all that. So that's going to be 4 squared, it's going to be 16. 1 squared is going to be 1, so that's going to be 16 minus 1, which is going to be 17. So modulus of z is root 17. Okay, for part B, find the modulus, the argument of z, giving your answer in radians to 2 decimal places. So I'm going to do a drawing for this one. It's a wee bit tricky, this one. So it's minus 4. So I'm going back 4 this way, and then minus 1 I. So that's going to be 1 down this way. Now, I'm going to call this wee bit alpha, but this is actually the argument of z in here. So it's all the way back from here. So I'm going to say tan of alpha is equal to 1 over 4, which means alpha is equal to, so how I've got this is tan to minus 1 of a quarter was 0.2449. So that means my argument of z, so I've just worked out this wee bit up here is 0.2449. So what I'm going to do is take that away from pi to find out what this angle is in here. So it was pi minus that 0.244, and which works out to be 2.90 radians to 2 decimal places. And then remember, it's back the way, so it's back this way, so this is a negative argument really. So just put a minus around all of that, and then it's minus 2.90 radians, and that's it. Okay, next thing is a modulus argument form of complex numbers. You can write any complex number in terms of its modulus and its argument. So Here you've got a complex number. Z is equal to x plus iy, and you could write that so that x part really is equal to, by a wee bit of trig, the x part is equal to r cos theta, and the y part is equal to r sine theta. So basically you can write it in modulus argument form. It's r cos theta plus I r sine theta, or you can write it as r upon cos theta plus I sine theta. We will see very soon the advantages of doing this, especially when it comes to doing things which we had seen previously in previous videos, things such as multiplying complex numbers or dividing complex numbers were quite a tricky process. When you have it in modulus argument form like this, it is very, very easy, as you'll soon see in one of the next videos. So very, very easy. So Z, the result then, you can write something complex, modulus argument form. Z now becomes r upon cos theta plus I sine theta, where r is your modulus and theta is your argument. Okay, anything else important here? It says this argument of theta is usually given in a range minus pi is less than theta is less than or equal to pi, although the formula works for any value of theta measured anti-clockwise from the positive real axis. Right, let's just jump on to an example. Last example for this wee bit of notes. The example says, and my example has disappeared somehow. How has this happened? Bear with me. And as if by magic it's back. So we've got Z is equal to minus root 3 plus I in the form r cos theta plus I sine theta, where theta is between minus pi and positive pi. So basically it says get it in modulus argument form. What you've got to do in this question is find the modulus, find the argument, and you're good to go. Okay, a wee diagram for any ones where it involves any negative bits. I would always do a wee diagram. If they're both positive, I probably wouldn't, to be honest, but definitely if there's a negative at all, I will, and you'll see why. Right, your diagram is like this. Clearly it's not a very good diagram, but I go back root 3 and then I go up 1, and we're going to draw a right angle triangle. That's your, call that alpha, but your arg z is this bit, which is actually in here. So we're going to find alpha, and then we'll be able to find arg z. Okay, first thing, before I find my argument, is I'm going to find my modulus. So r, remember, is just another way of saying your modulus of z, which is equal to, and it's going to be minus root 3 all squared plus 1 all squared, and the square root of that. So minus root 3 squared is going to be 3 plus 1 square root of all that, which is root 4, which works out very nicely just to give you 2. The next thing is to find our alpha first of all. So tan of alpha is equal to 1 over root 3, and that's a nice one they've given us. If you do tan to the minus 1 of 1 over root 3, you will get pi over 6 radians, and therefore your arg z is equal to pi minus pi over 6, which is 5 pi over 6. Okay, so you've got your argument and you've got your modulus. So you can write your thing in modulus argument form. So your answer is going to be 2 upon cos of 5 pi over 6 plus I sine of 5 pi over 6. Okay, that is us done, and you're now ready to do the following question. I guess maybe 2 exercises. Okay, so you've got 2 bits of exercises to do. You've got exercise 7b, a list of questions here, and exercise 7c. And that is us done.